Hello everyone, welcome to Calculus 2. Now we will begin this course with section 6.1 where we will begin to talk about integration by parts. Now this is a continuation of what we ended up in Calculus 1, which was integration by substitution rule. Now integration by substitution rule is very important, but this integration by parts builds on that. Integration by parts in some cases is very similar to the substitution rule, but it's more applicable to a variety of situations. So first, let's look at some of the integration formulas we had or we used in Calculus 1. And these are also mentioned in your textbook at the beginning of the section. The first one, and I'm sure you're very familiar with this one, is integral of x to the n dx is equal to x, increase this power by 1, divide this whole expression by the new power, which is n plus 1 plus c, of course, because this is an indefinite integral. It has no limits of integration. So we have to have plus c, which represents the constant of the antiderivative. And n, we want to make sure that it's never equal to -1. So that's just a condition that is given. The other integration formula that we saw, which is probably the most useful and easiest one to apply, is the integral of the natural exponential function is equal to e to the x plus c, of course. Another one we had was integral of sine of x dx equals, of course, minus cosine of x plus c. Integral of secant squared x dx, that is equal to tangent of x plus c. Integral of secant of x tangent x dx is equal to secant x plus c, and of course the integral of the hyperbolic sine x dx is equal to the hyperbolic cosine of x plus c, and also the integral of tangent of x dx is equal to natural log of secant x plus c. And another one, so we have more, but the inside cover, the inside of the back cover of your book has over 100 integral formulas. So please make sure that you also check those out as well, especially those of you who will move on to Calculus 3 later on. You will make use of that table a lot. And another integral is integral of 1 over x squared plus a squared dx is equal to 1 over a times inverse tangent of x over a plus c. And of course, these we have more. And I want to just list those same ones that your book has in this section. So we start with those, and I'll put those right here on this side. There's more of them. And so we have the integral of 1 over x dx is equal to, of course, natural log of x plus c. We saw this a lot in Calculus 1. And here's another useful one. The exponential function to base a is equal to, integral of that is equal to the exponential function divided by the natural log of the base. And I remember when I was taking Calculus 3 in my days, the multivariate calculus, which would be Math 283 on this campus, we use this a lot. So these are some of the very useful formulas. And then integral of cosine of x dx is, of course, sine of x plus c. right? And then a few more, we have a few more left. So integral of cosecant squared x dx is equal to minus cotangent of x plus c. All these minuses, I have to, it just occurred to me, just put them in red so they stand out, because we do not want to forget those, the minus in front of the antiderivative there. And so then the next one, we have integral of cosecant of x, cotangent of x dx is equal to minus cosecant of x plus c, and then integral of hyperbolic cosine of x dx is of course the hyperbolic sine x plus c, and of course all these c's indicate that we are integrating an indefinite integral. And then the integral of cotangent of x dx is equal to natural log of sine x plus c. And one last one that is also useful would be this one, would be the integral of 1 over square root of a squared minus x squared dx is equal to the inverse sine of x over a plus c, right? And that we know that a is greater than 0. Okay, so that's just a basic look at some of the integration formulas that are useful. So also from calculus 1, recall that we used something called the substitution rule, right? So let's do just one example just to remind ourselves, refresh our memory about what substitution rule was, because the integration by parts builds on that technique, and it expands on that to a new formula. So we're going to do just one example just to remind us. So also recall from calculus 1 that the substitution rule. And here's that example. Suppose we want to integrate this definite integral of e to the z power plus 1 divided by e to the z plus z dz, right? So in the integration by substitution rule, we learned that we take a look at the integrand and see if a piece of it can be written as the derivative of another piece of it. And in fact, in this case, we can do that. So here's the solution. So we take the piece that we want to take the derivative of as u. So let u be e to the z, the denominator, e to the z plus z. And if that's the case, then du would be e to the z is just e to the z, and a derivative of z is just 1. So plus 1 and all of that dz. Okay? All right, now, because we are using a new variable that is different than z, then these limits of the integration have to change as well. And they have to change according to this new variable. Okay, so let me write this down actually. So because So because the limits of the original variable u, original variable z, have to be adjusted or recalculated with respect to the new variable u. To be adjusted with respect to the new variable that we just introduced, new variable u. Okay. Again, this is just to refresh our memory from the last integration technique we learned in Calculus 1. Okay, this is just that. And so we have if z, because we have z, limits of z would be from 0 to 1, right? So then we move this up a little bit. So if z is equal to, let's start with the lower limit of the integration. If z equals 0 in this formula, therefore u would be, let's calculate this. So this would be e to the 0, right, plus 0. And e to the 0 would be 1. 1 plus 0 is 1. So u would be 1. When z equals 0, u equals 1. If z equals 1, the upper limit of the integration, then u, we have to calculate that. That would be e to the first power, or e to the 1, which is e plus 1. Okay, so now we have our new lower and upper limits of integration given the variable u. So let's rewrite the original integral. So what we have was this. First of all, I'm going to put this on so you have it on the screen. We started with integration from 0 to 1 of e to the z plus 1 over e to the z plus z dz, right? So we're rewriting this in terms of u, and the limits of integration changed from 1 to e plus 1, and we took u to be this denominator. So that's, and then the antiderivative, the derivative of that was the numerator, e to the z plus 1 dz, e to the z plus 1 dz. That's du. So 1 over u du would replace all of that. So 1 over u du. And of course, you already know how to integrate this, because this is actually one of the formulas we have. 1 over integration of 1 over x dx is natural log of x plus c. So let's do that. So this will be natural log of u, right? And going from 1 to e plus 1. Okay, so we can then evaluate this definite integral by taking the natural log of e plus 1 minus natural log of 1. Of course, this one is just 0. It drops out. And so we have just natural log of e plus 1. Okay. All right. So here's our final answer for that. So I hope this kind of refresh your memory about what the substitution rule was, and before we learn this new technique about integration by parts. So I want to begin our discussion of integration by parts by noting that this is similar to the substitution rule. of course, with more applicability to integrals. To integrals that are a mix of various factors. That's very important. So, like that, such as, so examples of that would include something like this: integration of t squared e to the t dt, or notice that this is we have a power function multiplied by an exponential function, right? These are various types of functions. And here we have a definite integral that is a factor of an algebraic function or a power function and a log function, natural log of r dr. Okay. So I want to just adjust the lighting. I'm not sure if you're, let me just try. And if the screen blacks out, don't worry, I'll just turn it back on again, but I want to, okay, so we were okay. So I'm just going to leave it like that. I thought the screen could be brighter. I'm not sure if, until I go home and look at the video of this capture, I don't know if your screen is clearly capturing all of this, but hopefully it is. Okay, so these are some of the examples we're going to use to apply the integration by parts. And as I said, notice that it's the types of integrals that are a factor of various types of functions. Okay, so then, but there is, so these are the basic steps. I want to give the basic steps for carrying out an integration by parts. Okay, so these are the general steps we're going to be using. So in integration by parts, the first thing that we do is we select a variable u, right? Just like the substitution rule that we used another variable. And that's where we start. So select a variable u to represent one of the factors in the integral. One of the factors, i.e. functions, in the integral. And so a good way of knowing which function to take as u, because if there's two, you kind of wondering, okay, how do I know which one to select as u? Well, there is some kind of a guideline, so that is useful actually, quite useful, that narrows it down pretty much. So we say that selecting u, selecting which function or which factor in the integrand will be u, can follow a systematic pattern, pretty much like the order of operations we used in basic algebra. So selecting u is easier when we follow this format, when we, or this order, when we follow this order. And this is from the highest order of priority. So if you have a logarithmic function you take that factor that is in the log form or natural log form as the u. Okay. The second highest priority is if we have an inverse trigonometric function the third on the list of the highest priority functions to be chosen as u is if we have an algebraic function and the fourth down the list is trigonometric. And the last one on the order of priority to be taken as u would be the exponential. Exponential function. So I just used the first letters to create a system of remembering this list, and let's call it L-I-A-T-E. L-I-A-T-E. Okay, so notice that the logarithmic functions are on the highest level. So if you have that, then you know you got to take that log function as the u. Okay, so that's how we pick that. Once we pick our u, the function that is going to act as u, then the second step is, and I'll try to fit all these steps on this page, we calculate du. We calculate its derivative of that function. We calculate du. Third step, so we select the rest of the original integral. Whatever we have left after we select our u, we select the rest of that, the rest of the original integral as dv. Notice we're introducing another new variable, v. So we select the rest of the integral as dv. The fourth step, we calculate the antiderivative of dv, which would be v, right? So we calculate v. Okay, fifth step is we rewrite the original integral as integral u dv, and finally sixth, we use the formula this formula, very important. So integral of u dv, which is our original integral written in the new variables, equals uv minus integral of v du. Okay, that's the formula we apply to step by step calculate our integral, original integral. So I'm sure we're all looking forward to examples of this. So this is pretty important, these steps. And I'm going to post all of this on Canvas so you can download hard copies of these lecture notes as well. If videos go too slowly for you, you can read the lecture notes. That way it would be faster. So that's It'll be up to you which resource you use, the videos or these lecture notes, or if you like, even both. So let's go ahead with some examples. The first one, let's always start with an easy example. So we want to integrate x cosine of 5x dx, right? Notice that this is a function of, this integral is a function of two factors, each function. We have a very simple linear function x here, and then we have a trigonometric function here. If I bring back our list that says which one to use as the u, that's the first step. That is the first thing we must do. We must pick our u. You select the variable u, and the way we select it is by look on the order of priority here. So algebraic function is higher on the order of priority for selecting a u than trigonometric function. So that tells us, notice that this piece is algebraic because it's just y equals x, or just a linear function x. And notice that this piece is our trigonometric function, right? So on this list, it says that algebraic function has a higher order of selection as u than trigonometric functions. So that means we're going to pick x as our u. Okay, so let's do that. So let u be equal to x, and then the second step was, what was it? Once we pick that, we calculate du. So take the derivative of u to get du. So we have du is equal to dx, right? So what was the third step? The third step was we select the rest of the original integral as dv. How's that? Well, the rest of the integral is what we have left. Cosine 5x dx, right? We already picked x as u, and we took the derivative of it, du dx. Now the rest of that is this. So we're going to pick the rest of this as dv. So let dv be cosine of 5x dx. What do we do next? Well, let's go back to our list here. Once we select our dv, we calculate v. How do we do that? V is the antiderivative of dv. So we simply take the integral of this. But the integral of this is really easy, right? It's pretty easy. So we know that the antiderivative of cosine is sine. But of course, by the chain rule, for this 5x, we would have a 5 coming off of sine 5x. So if we write v equals sine 5x, right? If this is the antiderivative of that, we must have a factor 1 over 5 as well here, because by the chain rule, when you take the derivative of this, you end up with a 5, cosine of 5x times 5. But this integral doesn't have a 5 in front, which means we must have had 1 over 5 at the beginning of in our antiderivative to cancel the 5 that comes from this 5x as we apply the chain rule when we take the derivative of that to get that. Okay? So this is the antiderivative of that dv that we selected. Now what do? Well, if we go back to our list, it says that rewrite the original integral as integral of u dv, and then use the formula that integral u dv equals uv, or u times v. By uv, I mean u times v minus integral of v du. So we're just going to apply this formula. Okay, and I will keep this on the screen so you can see. Well, I think that will be good here, like that. So you can see steps 5 and 6 as I apply it to what we have here. Okay, so the original integral was as follows. We had integral of x cosine of 5x dx equals now integral of u dv. U dv, which is equal to u times v. U is x, v is this. 1 over 5 times sine 5x, right? So we have 1 over 5 times x times sine of 5x. Okay, that's just u times v. U is x, v is that. We multiply them, we get that. Then the rest of the formula, minus integral of v du. What was v? V is that. Well, I have to put that 1/5 in front. So let me do that. 1 over 5. We can pull that outside of the radical, outside of the integral, right? So minus 1 over 5 v du. Du is just dx. Very easy. So we have sine of 5x dx. Okay? So now, this piece is fine, but this piece, we have to integrate this one yet, right? So, and that's an easy integral to obtain. We can easily do that. So I'm just going to take away that. So we start, we say 1 over 5 x sine of, remember that this is an indefinite integral. So at the very end, I'm going to have to put a c for constant, so plus c, right? So 1 over 5 times x times sine of 5x, and then minus 1 over 5, we need to integrate that. So this is sine of 5x, so we have to have had cosine to get this. But the derivative of cosine of 5x would be minus sine of 5x times 5, which of course is different than this. So we have to make sure that this minus is in front. So minus, to cancel that minus that comes from taking the derivative of cosine, multiplied by this minus, we get plus positive sign. So minus cosine of 5x. And then, of course, after that, we'll have to multiply this, all of this, by the chain rule, because we're going to get a 5. When we take the derivative of this, we get a 5, which, of course, we don't have, so we must have had another 1 over 5 here, okay, as we take the antiderivative of this. So if you're not sure, whenever you take the antiderivative of something, just take the derivative of this to be sure. See if you get that. If you get that, you're fine. You did everything correctly. But if you end up with something else, then you need to modify the antiderivative. So you want to cover your antiderivative like that and just take the derivative of this. Once you're done, see if what you have is equal to that. If you've done everything correctly, and if it doesn't match that, then the antiderivative is incorrect, and you have to revise it. But in this case, I'm sure if you take the derivative of this, you get derivative of cosine would be minus sine 5x, so that would make this positive. And then you're going to get a 5 by the chain rule, you're going to get a 5 from this 5x, but this 1/5 will cancel that out, so you end up with 1 here in front of the sign. Okay, so this should be correct. Now that we have taken all this, then let's clean this up. Let's simplify things, and then, of course, add c, because these are indefinite integrals. So the final result then is 1 over 5 x sine 5x. Minus times minus is positive, so plus 1/5 times that 1/5 is 1 over 25 cosine of 5x. And of course, this is all of this was coming from indefinite integrals, so plus c. Okay, so this is our final integral. And if you go back, review this, and see how much easier this integral became using applying the integration by parts. Let's do another example. And we'll make these examples progressively more demanding and more challenging in order to learn more and more techniques. Okay, so that's the only purpose of this. It's not to make it more difficult. It's just to learn more techniques. Okay, so here's the next example, which probably is similar to this. So we want to integrate x minus 1 times sine of pi x dx. Of course, notice that immediately that this is an algebraic factor, and this piece is trigonometric. And in that list that we had, it said that if you have a mix of algebraic and trigonometric, pick the algebraic one, pick the algebraic expression as the u, and the other one as part of the dv. So we're going to do that. So let's go with that rule. We're going to select x minus 1 as u. So let u be x minus 1. Therefore, du, of course, is just 1 dx or dx, right? dx. And then, of course, let dv be the rest of this, which is sine pi x dx. So we're going to have to take find the antiderivative of this, and that would be v. So that would be 1 over pi cosine of pi x, and of course, we have to have a minus, right, in front. So we have minus 1 over pi cosine of pi x. Okay, given that dv, that's the antiderivative. So now the next step is rewrite this in terms of u, what was it? Let's see. We had integral of u dv. Okay, so we have, I hope I can fit the whole solution here. I'll try. I don't want to move a part of it to the other page. So we have like this. Now u dv, integral of u dv is equal to uv, x minus 1 times that, minus 1 over pi cosine of pi x, right, minus v du. So, integral of v du. So that's the v. And du is just dx. Okay. All right. So, of course, you can see right away that this minus and that minus multiply each other, and we get a positive 1 over pi. Okay. So, all right. So we have that. Okay. So we're going to simplify this and of course calculate this integral here. So we have, let's bring this minus 1 pi in front. So we have minus 1 over pi times this x minus 1 times cosine of pi x minus times minus is positive. 1 over pi, I'm going to pull this 1 over pi outside of the integral. So what we have on the inside is just cosine pi x. How do we calculate the integral or antiderivative of cosine pi x? We have 1 over pi times times sine of pi x. Right? And of course plus c, because everything we're doing here so far has been indefinite integral. So like I was saying earlier, if you have doubts about this, just take the derivative of this piece and see if you get cosine or cosine of pi x. Okay, just take the, not that. This first 1 over pi is that one that I pulled out of the integral. But then if you calculate the derivative of this, what do you get? You get cosine of pi x times pi, right? By the chain rule, you get times pi. But we didn't have pi here, so there must have been a 1 over pi in front to cancel the pi we get when we calculate the derivative of this. So we end up with cosine of pi x. And again, this one is what we have here. Okay, so let me maybe, so this is that one. Now if you take the derivative of this, multiply it by this 1 over pi, you should get cosine of pi x. Okay, so I guess we should clean this up a little bit. Or simplify it, because 1 over pi times 1 over pi is just 1 over pi squared. So let's do that. So we have minus 1 over pi times x minus 1 cosine of pi x plus 1 over pi squared sine pi x plus c. And that is our final answer for that. Okay, so we have that. So keep this list in mind, this one, because as integrals get complicated, then this will help you in determining which of those functions you should take as u and which the rest of it you should take as dv, especially in calculus 3. Those of you who will move on to that, you'll get to, sometimes you get to complicated integrals where you're kind of, okay, which one do I use as u? So this will help you with that. Okay, so let's go over more examples of this type. So suppose we have, let's see, we have an example like this. We want to integrate t squared sine of beta t dt, right? So like before, just note that this is the power function, or I guess we can call it an algebraic function, right? We discussed these a lot when we were covering basic algebra. We talked about these and such, and polynomials and such. So this is an algebraic piece, and this one is a trigonometric piece of that integral or integrand. Okay, so, and we know from our list here that the algebraic functions take precedence to be u over trigonometric functions, right? So we know we want to take t squared as our u. By the way, it's at this point, since you've seen a couple of examples already, I'd highly suggest that I strongly recommend that you pause the video. It doesn't matter if you're fully confident at this point, what's important is that you write down your own solution before you compare it with mine. That's how learning happens. So if you're just watching this video or copying down these, it won't help you much. Maybe 10% effective, but the other 90% is when you pause the video and generate your own solution and then compare your solution with my solution, and if they agree, wonderful, you move on to the next example. If not, then you learn from that comparison. Learning is comparing your solution with mine. Just writing down my solution is not going to help you, or watching my solution is not going to help you at all, or it's going to help you very little. Let me just say that. So please make sure that you pause the video. I know I forget a lot to say this, but pause the video, write down your own solution, then compare your solution with what I have here. And of course, if the videos are too slow for you and you like a quicker pace, please download my lecture notes that I'm going to post all of this, so you can download those and just see what examples I have on there. Don't look at the solutions. Work out your solutions on a piece of scratch paper and then compare with my lecture notes. Okay? All right. So let's take, and if you're watching the video, then I'm assuming that you've already completed your solution and you're back, which is great. And you want to compare your solution with mine. So we want to take u to be t squared. Therefore, du, it's going to be 2t dt. Okay, by the same token, so the rest of this expression, the rest of that, we're going to have to take as our dv. So let dv be sine of b beta t dt. Okay, so let's integrate this to obtain v. So v would be, of course, minus 1 over beta cosine of beta t. Right? Like I said earlier, if you have any doubts about this, just take the derivative of it. See if you get that. If you get that, then you're fine. If not, then you need to tweak this a little bit so that when you take the derivative of it, you get that. Okay, so now we rewrite this original integral in terms of u dv and then the rest of it. So I'm just going to go directly to uv, from here to uv. Okay, so therefore we have the integral of t squared sine beta t dt is equal to uv, right? Let's multiply these. What do we get? We get minus, I'm just going to put the constant in front. Beta is some constant, right? So 1 minus 1 over beta, and then times t squared times the rest of this, cosine of beta t, and then minus, I'm just applying this formula right here, uv minus integral of v du, that's all. So minus v, which is that, du, that one. So I'm just going to say minus integral of minus 1 over beta cosine of beta t du is 2t dt times 2t, and I'll put the dt on the outside here. Okay. All right. So this first piece is okay. Of course, this piece needs a lot more work done to it. So, but let me clean this up a little bit. So what do we have? We have, so let me write this, minus 1 over beta t squared cosine of beta t plus, plus, I'm going to multiply this 2, minus is plus, and then 2 times 1 over beta, and I'm going to pull those two out of the integral, So we have 2 over beta in front of the integral of cosine of, or t cosine of beta t dt. Okay, this should do it. But of course, we're going to have to apply, I mean, let's call this equation, because we still cannot integrate this. So I'm going to call this, let's call this equation 1. Okay. Now we're going to have to apply integration by parts a second time to this piece again. Okay, so this, so we say apply integration by parts again to that. So that's easy now, because we know we're going to take u to be equal to t, and cosine bt dt will be our dv, right? So now we're becoming familiar with how this works. So then, once again, let u be equal to t, calculate du, which is equal to dt, then let the rest of this, which is be dv. So let me, so dv be equal to that cosine of beta t dt, and we're going to calculate v by finding the integral of this, of course, and that would be 1 over b again, 1 over beta again, 1 over beta times sine of beta t. Okay, so that should do it. And now, once again, we go through that cycle of rewriting this piece. So that's why I said let's keep this as equation 1. So let's not forget that we have that. And let's not forget that we have this 2 over beta in front. Okay, so we're going to have this. We're going to have all of that. So let me write that here. I hope I can keep all of this. I'll try to keep this on the screen as much as possible. But let me rewrite this. We have 2 over beta integral of t cosine of beta t dt is equal to this 2 over this factor, 2 over beta, times, now we're going to construct our integration by parts, pieces of our integration by parts equation, which is uv. So that would be 1 over b times 1 over beta times t times sine of beta t. That's our uv, right? And then minus, let's see, so 1 over, okay, so that should be okay, minus v integral of v du. So this is v integral of this piece du, which is dt. But we have this constant, so I'm going to put that in front again. 1 over beta integral of sine of beta t dt, because that's du. V minus v du. Now we have it. Okay, and I'm going to close this bracket. Okay, so now when we take the integral, we're going to end up again for sine, you integrate sine of beta t, you're going to end up with minus cosine of beta t times 1 over beta. Okay, so let's do that. So I'm just going to carry this 2 beta times 1 over beta t sine beta t. Now I got to be careful. So we have minus 1 over beta times minus cosine of beta t times 1 over beta. And there we have it. Okay, that should be okay. Okay, so let's then let's distribute this to all of that, and let's see what we get. We're going to get, so we're going to get 2 over beta squared t sine of beta t minus times minus plus 1 over beta times 1 over beta, 1 over beta squared, and then well, 1 over beta times 1 over beta is 1 over beta squared, but times this one, since we're distributing this 2 over beta again, as we did here. So we're distributing this factor to each term. So we're going to get, let me change this to beta cubed, so 1 over beta cubed, positive, and then times, and of course the 2 as well. So since we're distributing, let me also change this to 2. So 2 over beta cubed times cosine of beta t, and that should be okay. And of course, I'm going to add c at the end, but let's call this our equation 2. Equation 2. Okay, so we had equation 1. The first piece we need to keep, we need to bring down to the final answer and incorporate this in. This is part of our final answer. But we had to apply the integration by parts again to this piece, right? So now let's combine that with the rest of this. So you're not seeing that first piece on the screen anymore, I know, but I'm going to write it down here as the final answer. The final answer is the combined equation 1 and equation 2. So we have minus 1 over beta t squared cosine of beta t, and then this piece that you can see on the screen, plus 2 over beta squared t sine of beta t plus 2 over beta cubed cosine of beta t, of course, plus c. Okay, so all of that. So let me box this. So that's basically the final answer for us. And let me, so here we have the minus with dt, everything looks good. So 2 over t sine of beta t plus like that. Okay. All right. So I hope this agrees with the answer that you have. If not, now is the time to compare this, correct or add or subtract from your own solution to see, to match these steps and to see if you can learn in which step you went stray from the solution. So you can definitely learn from that when you compare solutions. Sometimes you might catch my errors, and then of course I count on you to let me know, and I'll be happy to record a corrected video. Okay, that would be good too. Okay, so let's go over another example. Here, we're going to make the transition. Notice every example that we've done, it was with indefinite integrals so far, just like this one. We're going to transition to definite integrals. So we want to integrate from 4 to 9 of natural log of y over square root of y dy. Okay, so as we learned in Calculus 1, whenever you have a square root, it's better, I mean, of this type at least, of this type, it's always better to write it with a power, with a rational power of some kind, And it's easier that way when you calculate the antiderivative or the derivative of this. So let's rewrite this in that fashion. So we have, so this is what we want to calculate, and so let us write this as integral from 4 to 9 of y to minus 1/2 power, right? That's just that piece written in this form, times natural log of y dy. Okay. Of course, what we have here is that this piece is the algebraic piece, and this piece is the logarithmic piece. And let me bring that nice list that we have. And it said that when you pick the u in the integration by parts procedure, logarithmic expression has the highest priority to be selected as u. Okay, highest priority. So in this case, we're not going to use as that. We're not going to let u to be this. We're going to take natural log of y to be our u. Okay, so that list is handy for us to pick the right variables here. So let u be natural log of y, and of course we know that du would be equal to 1 over y dy. And so then dv naturally would be the rest of this, which would be y to the negative 1/2 dy. So let dv be y to the negative 1/2 dy. Okay, and this would be, so from that, v is simply add +1 to this, divide this whole thing by the new power. So we have 2y to 1/2 power. Okay, so now let's rewrite our integral here in the new form. So we have integral going from 4 to 9 of y to minus 1/2 power natural log of y dy equals uv, right? We start with that, u times v. So we have, and this is definite integral, so I have to remember to put the limits of the integral for each piece. So uv would be natural log of y times 2y to 1/2 power, right? 2y to 1/2 power, and then this goes from 4 to 9, okay? And then of course minus v du. So let's put all that. So this 2, I'm going to put that in front, and then integral of v y to 1/2 power times du. So this would be 1 over y dy. Okay, that's du. All right. So let's see. That's an easy integral to calculate. Some of you might choose to calculate this already. It's fine. I tend to keep this, and when I'm done with this piece, then I'll calculate everything at once when I have definite integrals like this. But you don't have to do that. You can calculate, if you like, you can calculate this and then at the same time manipulate this according to the integration rules. Okay, it's up to you. But don't be surprised if you see me keep this going. So natural log of y, and I can write it 2 square root of y times that too. I'll do that next. Natural log of y times 2 square root of y, going from 4 to 9. And then, so here we have y to the negative 1 power. The bases are the same. So what do we get? If we combine this, we get y to negative 1/2 power dy, right? I just wanted to combine those before I integrate. Okay. All right, so next step, we have now 2 square root of y times natural log of y, going from 4 to 9. Now let's integrate this. What do we get? We get minus 2, and then add 1 to this, divide the whole thing by the new power. So we get positive 1/2 divided by 1/2, that's 2. So we have 2y to positive 1/2 power going from 4 to 9. Oh, I'm sorry, I should remember to put these, I forgot to put these also. Okay, so this is, whenever I forget something and I have to add it in my videos, I like to do it with red ink so you can see that those are pitfalls that we should not forget. So I added it like that. All right. At the end, I would have caught it, but it's better not to have it in the middle anyway. Okay, so now we can, if everything is done, then we can then go ahead and apply these limits. By the way, that's also square root of y, right? So let me do that. So 2 square root of y, natural log of y, 4 to 9 minus 2 times 2 square root of y, going from 4 to 9. Okay, so applying the limits of the integration for each piece. Here we have 2 square root of 9 times natural log of 9 minus 2 square root of 4 natural log of 4 minus 2 times 2 square root of 9 minus 2 square root of 4, right? That's everything. So then what do we have? We have square root of 9 is 3 times 2, that's just 6. 6 times natural log of 9. Square root of 4 is 2. 2 times 2 is 4 minus 4 times natural log of 4. And then we have a minus 2 outside here. What do we have on the inside? We have 3 times 2 is 6. And so 6 minus 4, that's 2. That's 2. That's just, 4 is 2. So that's almost, we're almost there. 6 natural log of 9 and minus 4 natural log of 4 minus 4. And that's our final answer in this case. Okay. I hope this is starting to make sense, and I hope you're pausing along the way before you're seeing my solutions. Okay. My solutions are really honestly worthless until you have your solutions, because your solutions make these solutions valuable, because then you can compare. But by themselves, my solutions are worthless. Okay? All right. So the next example, let us then go through, well, this page was 6, so this has to be 7. So we want to go over this example. This is a little bit, so this is involves an arctangent. It's good to see one of these inverse tangent or inverse trigonometric functions in this process. So we want to calculate the definite integral from 1 to square root of 3 of arctangent. This is, by the way, inverse tangent, right? Arctangent of 1 over x dx, right? So this is the question that we have. All right. So some of the things we have to remember are well, one thing that we should remember from the past, so this would be part of the solution, is that recall that recall that the derivative of inverse tangent of x is equal to 1 over 1 plus x squared. The reason I say this is because if we look back at our list, right, so we only have inverse trigonometric, after logarithmic functions, inverse trigonometric functions have the highest priority to be selected as u, right? They're the second on the list, right after logarithmic. So we want to take all of this as our u. If we take this as u, then we need to know what is the derivative of u, right? du, in order to calculate du. So now we know. If you remember this, then we can easily calculate the derivative of it. So now that we know that, let u to be arctangent of 1 over x. And then we got to be careful because this 1 over x, by the chain rule, has a derivative that we need to multiply by that. Okay? Because the derivative of x is just 1, but we don't have that. We have 1 over x, so the derivative of this would be minus 1 over x squared. So we just have to remember to multiply that by the chain rule. So du then is equal to that, right? Instead of x, we have 1 over x, so we'll just replace it. Equals 1 plus 1 over x squared, right? Instead of x, we have 1 over x, so we're going to substitute. And then by the chain rule, the derivative of 1 over x is, so we have all of this, and then minus x2 minus 2 power dx, of course. Okay, let's clean this up a little bit. And so we have du is equal to this minus, so I'm just going to say minus 1 divided by 1 plus 1 over x squared, 1 plus 1 over x squared, times, let's just write this x2 minus 2 power, let's just write it as 1 over x squared, I guess. So times 1 over, and this minus is already here, 1 over x squared dx. Okay. Oh, now, so we can simplify this a little more, right? Look at it. So we can distribute this x squared into this denominator. So let's do that. So du is equal to minus 1. Distribute this x2 times 1, it's just x squared. Or x squared times 1 is x squared. X squared times 1 over x squared is just 1, right? Like that. So that's much better than all of that. Okay, now that we have that, what would dv be? If we picked u to be all of that, what is dv then? Very easy. dv would be dx. Okay, so that's pretty straightforward. Let dv to be equal to dx, therefore v is equal to x. Now we can apply the integration by parts to our original expression, which was integral from 1 to square root of 3 of arctangent 1 over x dx is equal to u times v. That's the first part, right? U times v, which is x. So x times arctangent of 1 over x. Let's write that up. So we have x times arctangent of 1 over x. Of course, this is a definite integral, so it goes from 1 to square root of 3. Then minus v du. V was just that v is x, right? Where is it? Okay, so v du, which is all of that. So we have minus integral of minus 1 times x. That would be, so I'm going to, well, so it's like this, minus x over x squared plus 1 dx. Okay, but I don't want to have this negative dangling there, so I'm going to multiply these and make this positive. Let me do that. So equals, oh, by the way, so this goes from 1 to square root of 3. And so we have x arctangent of 1 over x going from 1 to square root of 3 plus integral from 1 to square root of 3 of x over x squared plus 1 dx. So now this takes us back to substitution rule, right? Because look at this. If we let u, we select another, going back to calculus 1, if we take the denominator as u equals x squared plus 1, then du would be 2x. X is something we have in the numerator. All we have to do is just say 1/2 du would be x dx, right? Let's do that. So for this piece, applying the substitution rule, from calculus 1, right? We remember that. I may have to move the rest of this solution. I don't think I can fit it all on the rest of this page, but we'll see. We have, this is what we have. We want to set, let u be equal to that. Oops. Let u be equal to that, x squared plus 1. Therefore, du will be 2x dx. But we have x dx, right? We have x dx. We don't have 2x dx. So how do we get rid of this 2? We multiply both sides by 1/2. So 1/2 du equals x dx. Now x dx is equal to 1/2 du. And we can put it there, and the rest is easy because we're going to have 1/2 1 over u, and 1 over u has a very easy integral, which is natural log of u, right? So okay, so now we can put it all together. So let us, oh, by the way, so I used an example from the substitution rule at the beginning of this lesson. So now that we've transitioned, because this is substitution rule, so it's different than a little bit different than the integration by parts. We introduced the new variable u, so the limits of integration are going to change, right? So let's calculate what those limits of integration are. So if x is equal to, I'll just start from the upper limit this time. If x equals square root of 3 and we plug it in here, what would u be? U would be square root of 3 squared, that's 3, plus 1, u would be 4. Okay, just calculating u from this, with x being square root of 3. Now, if x is equal to the lower limit, 1, then what would u be? U would be 1 squared plus 1, that's just 2. So these are the limits, the new limits of our integral that I'm going to write next. Okay, so we're going to go to the next page. As much as I didn't want to do that, I prefer to put all the solution on one page as much as possible. But let's see if I can, maybe I can keep some of this on the screen as we do this. Okay, I'll try to like that. Okay, so that's better. but then I'll remove this sheet as soon as I'm done writing it. But I wanted you guys to see this as we write the next step. So we have, and this would be page 8, so we have, again, we have x, arc tangent of 1 over x, going from 1 to square root of 3, right? Sorry about that. I know it's at the bottom of the screen, but I'm trying to keep all of that on the screen as well. Okay, like that. And then plus, I got to be careful here because we're transitioning from x to u. So the limits are no longer 1 and a square root of 3, but they're 2 and 4. So 2 to 4. And then we have 1/2, right? Notice this 1/2 du equals x dx. So this x dx is equal to 1/2 du. But I'm going to put this 1/2 on the outside and in front of our integral, right there, 1/2. And then I'm going to write 1 over u du. Okay, 1 over u du. Okay. I hope that makes sense to you. If not, please let me know. I'm counting on you to let me know if you have any questions about that. But I think that step was clear. Okay, so now this is a pretty easy integral to deal with. So we have x arc tangent 1 over x going from 1 to square root of 3 plus 1/2 from 2 to 4. Okay, that's just integration of that. And okay, so now we can apply the limits of the integral and calculate the final result. So we have, in one piece we have square root of 3, right? Square root of 3 arc tangent of 1 over square root of 3. I'm sure you recognize this 1 over square root of 3, if you rationalize the denominator, it's square root of 3 over 3. So inverse tangent of square root of 3 over 3 tells us we're dealing with angle pi over 6 or 30 degrees, right? We'll get to that in a second. Then minus, now substitute for x with 1, we have arc tangent of 1, and the tangent of pi over 4, of course, is 1, so we know that. And then plus 1/2, and then let's apply this. We have natural log of 4 minus natural log of 2. Okay, so that's just in case they're negative, but we don't have to use the absolute value since we know 4 and 2 are positive values. Okay, but I'll remove the absolute values in a second. All right, so now let's calculate these. So we know that this here, this is just pi over 6. That angle is pi over 6, and this angle is pi over 4, right? And then the rest we can easily obtain from that. So we'll keep these as they are. Let's not calculate the decimal values. It looks better like that. I mean, it not only looks better, but it's more exact if we keep it like that. And then, so we have square root of, so we have square root of 3, or pi square root of 3 over 6. And then we have minus pi over 4. And then plus, plus 1/2. We know from Math 124 and Math 126, early algebra classes, that we can write the difference between two log expressions as a division, right? We can convert this difference into a division. So times natural log of 4 divided by 2, we can write that as that. Then, of course, this is 2, so we have pi square root of 3 over 6 minus pi over 4 plus 1/2 natural log of 2. And that's as far as we can take this. So all of this, and we have that final answer. Okay, I hope this matched what you have in your solution. All right, so let's do another example. And I'll just start a new page. I don't think I'm going to be able to fit all that on that page. So in all right, so for this example, we want to first, this is actually a very important hint that they give us in the problem statement. It says first make a substitution, then use integration by parts to evaluate the integral. So this substitution refers to that a technique we've used before. So do that, make a substitution, then use integration by parts. So very important hint they give us there. So when we look at when we have a statement like that, looking at this expression, it's better to have similar terms when we have a substitution case. So for example, here we have theta squared and theta cubed. If we can get similar terms in our expression, that would be a better way of applying the substitution method. So notice that if I break up this theta cubed to theta squared times theta, then I have created a theta squared, which is similar to the argument of this trigonometric function. So let's do that as the first step for us to use the substitution before using the integration by parts. So we're going to write let's break that apart. So we have, instead of theta cubed, we have theta squared times theta, then times cosine of theta squared d theta. Okay? So look at that. We've created similar terms here in the expression. Now they're they're telling us to use substitution, so let's do that. So if we take, let's say, x, not u, right? U is for using integration by parts. Let's say if we're using x, some other variable than u. So let's say x equals theta squared. Okay, so let x be equal to theta squared. Again, we're not yet applying the integration by parts. With this substitution, then immediately what will happen is that if we take the derivative of both sides, we get dx equals 2 theta d 2 theta and then d theta. right? That's just taking the derivative of both sides after using this substitution for theta squared using x. Now, compare what we have with what it was in the expression. So theta squared can be replaced by x. Then we're going to be left with theta d theta, right? Theta d theta. So here we have dx equals 2 theta d theta. So we have this 2 extra. So how do we get rid of this? Multiply both sides of this derivative by 1/2. So we're going to get 1/2 dx equals theta d theta, right? So now we have something, a replacement in terms of x for theta d theta. Okay, so now let's substitute, but if we're going to substitute x for theta squared, guess what happens? What else do we need to do? And we talked about this in Calculus 1 extensively. The first example that I gave as a refresher at the beginning of this lesson dealt with that too. Whenever we're using substitution, we need to recalculate the limits of the integration. So what we'll need to do is say that if theta is equal to the lower limit of the integration, or square root of pi over 2, right? If theta is equal to that, then what would x be? Therefore, x is this squared, right? Theta, square root of theta, square root of pi over 2 squared, which will give us pi over 2. Right? So let's calculate the upper limit for the new variable x, because we're using substitution. So if theta is equal to the upper limit, which is square root of pi, then x we can calculate using this substitution equation. We have x equals square root of pi squared, which is pi. Okay, so these are the new limits of the integration after we replace theta and d theta with x and dx. Now let's do it. So now we have, after all this, we can substitute and we get this new integral with lower limit going from pi over 2 to pi, right? And instead of theta squared, we have x. Cosine theta squared would be cosine of x, right? And then theta d theta, we have instead, what do we have? Half dx. So this half, we know that it's a constant, so let's put it in front. So we're going to put that 1/2 here. And then we can just replace theta d theta with the rest of this, which would be dx. Now look at that, how easy of an expression that is, rather than dealing with this original expression without the substitution. So this hint they give us to use substitution before integration by parts is pretty important. All right, now we can use integration by parts. We have an algebraic piece, which is x, and we have a trigonometric piece, which is cosine of x. So we know that the trigonometric function has a higher order of priority as being selected as u for integration by parts. So let's do that. So let u be cosine of x. And then based on that, du would be, oh, sorry, no, let me correct this. I meant that algebraic equations have a higher priority than trigonometric functions. I stand corrected on that. Let me, for now, I'm just going to do this, but before I post this on Canvas, I will clean this up. I will clean this up so that it looks nice and neat. But Algebraic expressions have a higher order of priority than trigonometric functions, so u equals x, so therefore du equals dx. Then next on the order of priority for use in the integration by parts would be picking the dv, which would be the rest of this, right? It would be cosine of x dx. So dv equals cosine of x dx. Therefore, v would be simply sine of x. Okay? And with the new integration limits, of course, coming from our substitution. All right, so now let's apply the integration by parts to this one. So I will put an arrow from here to here. So the red arrow indicates substitution. The blue one indicates applying the integration by parts. So we have, we want to do let, then this, the original one. So we have, let me, 1/2, let this integral be equal to its equivalent when using the integration by parts, which would be u times v. So we have x times sine of x. Of course, having these limits of integration, so from pi over 2 to pi minus. So when I do this, one thing we should remember, so let me put this in a little bit, shade this in red. So this 1/2, because the integration by parts is going to apply to all of this. So 1/2 times all of that means we have to have a 1/2 in front of all of this. And I will put a red parenthesis here, like that. So 1/2 times everything we do in the integration by parts. So then we have integral from pi over 2 to pi of v du. So that would be sine of x dx, right? And let me close the parenthesis there. Okay, so we remember that this 1/2 is in front, and we carry it over. All right, so let's simplify all of this and integrate this, which is pretty easy to do. So we have 1/2, that's that 1/2, times x sine of x going from pi over 2 to pi minus, this would be minus cosine of x going from pi over 2 to pi, right? And of course, this minus times that minus will give us a positive there. So let me also account for that. So we have 1/2 times x sine x pi over 2 to pi plus cosine of x pi over 2 to pi. And now we're ready to evaluate the integral after we've integrated this. So just plugging in, we have 1/2. So this would be pi sine pi, right? Like that. Move this down a little bit. Pi sine pi minus pi over 2, just plugging in the pi over 2, sine pi over 2, right? Then we have, so that's that, and then we have, of course, plus, then we have this piece. So we have cosine of pi minus cosine of pi over 2. And we can do that. Okay. All right, so I'm sure you quickly notice that that one is 0 and drops out. Sine of pi is 0 times pi is 0. And also this one, cosine of pi over 2 is 0, so that term drops out. So we are left with 1/2 times pi. Sorry, no, not. That one drops out. So minus pi over 2, and this is 1. So this is 1. So minus pi over 2 times 1 is minus pi over 2 actually, minus pi over 2, the result of all of that, plus, what else do we have here? That one dropped out. Cosine of pi is, of course, we know from trigonometry that it's equal to minus 1. So plus minus 1. Okay, so the final result, let's just distribute all of that. We will get minus pi over 4, 1/2 times minus 1, minus 1/2. Okay, so here is the final result for that initial integral. Okay, so I thought this was, your textbook gives a few examples like in the back of this section, or if it has a few questions about applying the integration by parts after you've made substitution. I think these are very good examples, and especially in Calculus 3, you're going to see a lot of examples like this. So I hope this video was useful, and thank you for watching the video until this point. And please don't forget in our future video lessons to write down your own solution before you watch my solution for an example. For now, have a nice day, and I'll see you again next time.